Okay, so here's my second derivative and the critical values. I'm going to put them on my number line here. X equals 0 and x equals 3, and I'm going to make a sign diagram for my second derivative. Now, at 0 and 3, the second derivative didn't exist. I don't know what's going on there. So I'm going to pick some test values. And I'm going to figure out what the sign of these are. If I plug -1 into the second derivative, what am I going to get? Well, the numerator is always going to be negative, so there's no helping that. Let's look at what the denominator has in store. I'm going to take a number x. This means to take the cube root of x. This means then to take the fourth power. So regardless if this is positive or negative to start with, that fourth power is going to make everything positive. So in particular for -1, I get a positive in there. This factor, if I plug -1 into it, I get a negative. The cube root of a negative is a negative. The fifth power of a negative is also a negative. So guess what? This gives me a negative down there. So the long and short of it is, I get a negative over a positive times a negative. That gives me a positive. Let's plug in 1 to the second derivative. Does anything change? Well, as we mentioned before, these two factors are going to always be negative and positive, respectively. I plug 1 into this quantity. 1 minus 3 is negative. The cube root of a negative is a negative. To the fifth power is a negative. So guess what? That stays a negative, which means it's positive here as well. Finally, I plug in 4. Does anything change when I plug in 4? Well, this is negative and this is positive all the time. But now when I plug 4 into here, I now get a positive number. So a positive number to any power gives me a positive number, which means that the second derivative is negative there. Okay, so what's this mean for my original function f? Well, it's concave, or this is positive. That means it's concave up. Don't know what's going on there at 0. It remains concave up. Don't know what's going on at 3, but then it changes to concave down. Okay, so for intervals being concave up, I've got -infinity to 0 and 0 to 3. The question is, can I combine those? And the answer is no. And the reason why the answer is no is that the first derivative, 0 and 3 aren't in the domain. So I can't connect things up. It's not, x equals 0 is not in the domain of f prime of x. So we're going to list these as separate intervals. Remember, concave up means that the first derivative is increasing. So this means that the first derivative itself is increasing on these two intervals. Is it fair to say it's increasing over the entire interval 0, 3? Well, we can't really make that claim unless we know what's going on at 3, or at 0 rather, in the first derivative, and the first derivative is not defined there. Okay, so it's not in the domain. So we can't connect those up, once again, because 0 is not in the domain of the first derivative, even though it is in the domain of the original. Concave down from 3 to infinity. Are there any places where it changes inflection? Or excuse me, it changes concavity? Yeah, it changes here at x equals 3. Now to be an inflection point, we have to make sure this point is in the domain of f. As we talked about earlier, the domain of f was all real numbers. So there is an inflection point. So f has an inflection point at 3 comma f of 3. And let's remind ourselves, what was the f of x? I'll just sneak it in up here. F of x was x to the 2/3, x minus 3 to the 1/3. So when I plug 3 into that, I get a 0 out. All right? So that'll do it then for quiz 12.